if I went to mile marker 57, I want to know the distance in miles would be 57 minus 51, right? It would be a positive value. This is not always the case. Now, here it's 0.25 is the mile marker I'm going to land at for the voltage maximum. Do you all see that? When I take this and I subtract that from here's where I land, here's where I started. So now I say I have 0.25, that's the mile marker here. Then I subtract off where I started at, which is 0.3, where's that? 45?
Yeah.
45, this is all in terms of lambda. Well, that's negative. That doesn't make sense. So then you add a half wavelength. If you get a negative value there, where you ended up, from where you came from, you add a half wavelength, or 0.5. Now what's this value going to be?
0.40, 0.405.
405, about 0.4. That's exactly the distance that we moved from here to here. Now I can tell you another way to do it. I know if I move from here back to here, it would be exactly 0.5 all the way around. Do you agree with that? We start here, when a half wavelength, I'm back at this point. So if I know that, if I just subtract off this distance from a half wavelength, then I get the distance to that point. That's 0.25, that's 0.345. It's roughly what is that, one something, right? And you would subtract that and you would get back to here. That's another way to do this. But you all with me on this class? So that would be how you would get the distance you'd go from here to here. Anytime you're moving and you want to know if it's wavelengths towards generator, from where you start, subtract off where you finish. If it's negative, add a half wavelength. That's it. Okay? Now, is there another part to that problem or not?
It asked for the load impedance.
So
we started for that.
Well, yeah, but, I mean, go ahead.
And then we found the Viswar and the measurement frequency.
No, I think that's
Yep.
it.
That's it? Okay. You all follow me on that? That's a tricky one, by the way. Because you haven't really thought through the Smith chart business. You always start with a load, right? Now we had to calculate the load. We went backwards, you might say. Reverse engineering. What's another problem? That's a good problem. Thank you.
The next one that I had was 2.33.
All right, let's do that. Did you guys understand? I like the way I explained this here. You with me on that? What don't you understand though?
I get kind of lost when you say you got to go all the way back around.
Yeah, well, why did you go?
I wanted to find out how far it was to the voltage maximum. That's the only thing I was doing.
Well, why'd you go wavelengths towards generator instead of wavelengths towards load?
This is the load, right?
Yeah.
The voltage maximum is going to be.
Oh, okay.
If you're at the load, you can only move towards the generator.
Yeah, yeah.
That's the reason. All right, that's the reason.
You go all the way around.
Yeah.
Okay.
Yeah.
All right. Let me get the next one. But if you have another question, by the way, this takes some time. You got to spend time on this. Random takes a lot of time. This takes time because unless you really comprehend what's going on, you'll mess up the questions left.
We solved for that last number, 0.405.
Huh?
We solved that last number, 0.405, right? What's the significance of that number?
Well, think about in that graph, just for a second. This is not going to be done too well. Here's the 5.5 centimeter point. That's where the load is, right?
Yeah.
All right, if you look, there was something where he had like this, and there's a maximum over here, right?
Yeah.
If you move from here and you added the distance from the load point and that, what was it, at point, you're going to get this distance, which is going to be, here's the halfway point, right?
Yeah.
All right, well, I forgot what that was, around 4, right? 4 centimeters? Well, if I take 4 centimeters and I add the wavelength, 7.5, I'm at 11.5 centimeters, right?
Yeah.
That's what the maximum was. It's not shown on this graph.
Yeah.
All right, so what I'm showing you is if you go from here and you move in terms of wavelengths, 0.4, what was it?
0.05 wavelengths.
Point what?
0.405 wavelengths.
All right, if you take 0.405 wavelengths multiplied by the wavelength, which is 15 centimeter, then you're going to get this distance, which is going to be half wavelength, which will be 7.5 centimeters. That tells you how far you have to move until you hit. If we just plotted this thing out, it would keep repeating itself. He doesn't show you where this peak occurs. You know what I mean? How far is it occur? Well, I know that was where the load is, right? That's this point. So I'm out here. I go all the way around height. At this point, that's where I know the maximum is going to occur. How far did I go? Well, I moved from here all the way up past the end of that graph until I hit a peak out here, which is going to be whatever this comes, 0.405 times the full wavelength.
And so that gives us the distance to the maximum.
That's right.
what we're
That's
shooting
right.
for. Okay.
Yeah, and by the way, I don't like this problem because it shows you stuff that's really not there. I mean, if the load's here, why are you showing me this?
Probably because he used a different method, I think.
No, it's called, this is a standard way where you measure, it's an airline, and they just put the load anywhere inside there. And then they measure the viswar by a probe, measuring the voltage at the outer and inner core of that airline. And then they'll go ahead and just graph it, and they'll have the students, this is a long time ago they used to do this, have the students figure out what the viswar was, what the load's value is, all the stuff we just did. But really, in the real world, you don't have, when you hit the load, that's it. It doesn't continue in the real world. All right, now for this next one, did you understand this now? All right. Keep in mind, the key thing is going through these problems systematically, and anything you don't understand, write it down and ask me. Because there's going to be some stuff that you're going to, trust me on this one. It's just inevitable. All right. So, next, and this is the way you learn it doing problems. I don't care. I can go through lectures till I'm blue in the face, but until you apply it, you really won't see how this stuff all works. All right, so tell me the next one. Go ahead.
Referring to figure
3-1?
Referring to figure 2.2, this is 2.33, but it's referring to figure 2.25, which is on page 77.
Here, I'll get it.
On 77?
Yeah.
Hold on. 77, got it.
It gives Z in SC and Z in L, and we define the actual load impedance, and then we get Z naught 2.
Zn at C?
Do you see Z in SC and then Z in L on figure
the
figure 25, 2.220?
for the short circuit shown.
All right, hold. I got it right here, so I've got it.
So it gives
Go ahead. Just read the
Z,
problem.
okay. Referring to 2.25, suppose we measure Z in SC equal to plus J25 ohms and Z in L equal to 35 plus J85 ohms. What is the actual load impedance? Z naught is 50 ohms.
I think something read wrong.
It's 2.25 is all three of these figures on the page. So the ZIN SC is defined at the top with the transmission lines.
Yeah, if it's short circuit, they have a measurement, then it's then it's the load, right?
Yeah.
Okay, guys, this is not that bad, but I'll show you what he's talking about. So he's got a transmission line. And he says for part A, at least, it's a short circuit, right? Mm-hmm. And he measures the input impedance here, right? Does he give you the length or not?
Nope.
No. Does he give you the characteristic impedance of the line?
50 ohms.
So this is Z naught equal 50. Now just watch this. So we don't know the length of line L, right? We can do it with a Smith chart, but I want to just show you this. Two ways to do it. One is this. We know that Zn, we can do it with the Smith chart in a second, is Z naught times Z load plus J Z naught times the tangent of beta L over Z naught plus J Z L, tangent of beta L. That's one way. Over here when we have a Smith chart, and I'm just drawing a crude drawing of this, here's my Smith chart, right? This is really infinity, this is the 1 point's the center, J1 minus J1, all right? Now, over here he says when it's a short, what do we get for Zn? This is part A.
It is J25 plus J25, yeah.
Pardon me? J25. You all hear me? Okay. Now look over here. For this to have a value of J anything, well, let me do it here first. He says it's J25 25 at the length. So J25, this is normalized, so it's actually a value when we talk, take a look at that. If that's the Zn, the normalized Zn right here would be J25 over 50. You all follow me on this? That would be the normalized input impedance, because the load impedance we always start with by dividing by Z0, and we get the normalized value, correct? So this is the normalized input impedance, which is really going to be J1/2, right? Y'all hear me?
Yeah.
That's the input impedance we measure. Here you go. Now, where is that? Take a look on your Smith chart. You see how J1/2 is about here. Take a look. Or you might call this J0.5. You see where this trajectory intersects this and it's got a value of J? Like J1 is right here. J.5 is about there. Can you all see that on the rim?
Yeah.
Right?
Yeah.
Now, that's where we came from. Now listen carefully. What was the impedance, normalized impedance of this load? Just think about it for a second. It's a short circuit. What's the value of impedance for a short circuit?
0.
0, right? Normalize it. 0, right? 0 divided by 50, divided by 100, divided by anything is still 0. Do you agree with that?
Yes.
So where's that point on your Smith chart? That's right here, isn't it? Isn't that 0? Take a look. Just make sure, can you see it back there? All right. Now, how far did I move? Well, I moved the length of the line from here to here. Now, here's where you're going to tell me what the length of the line is. Y'all see this right here? All right. This point is at 0 wavelengths. If you look, right? What's this point? You go from the center, you shoot a line through there, and tell me what you read wavelengths towards generator here. What is it?
Around 0.065.
Take a careful look, everybody. You see it right there? Look at that. You don't have a, do you have an extra Smith chart you can give him?
I can give him this picture.
He's, I know the feeling. Y'all with me? Can you see it, sir? Can you see it?
Oh, yeah.
Do you see it back there?
Yeah.
You got it?
0 to...
You see it back there? All right. So that means the length of the line, this is 0.065, right? That's 0.065 lambda. That's the length of the line. L is 0.065 lambda long. Now we've got the length of the line.
Because...
Yeah, because he gave us, this is a short. We know what ZL is. You normalize 0 divided by anything, 50 is still 0. This is the point you come in at, right there. That's 0 ohms. Can you all see that?
So we moved from ZL to ZL of 0 ohms all the way to...
Why did we move that way? Because he said that's the input impedance, right?
Yeah.
If the normalized input impedance is J1/2, so that's this far. So here's where we came in at. That's the load. We know the load, and we moved to here. So now we have the length of the line, which is 0.065 lambda, correct?
Mm-hmm.
Now, the next part is he says I stick a load on it. Now just watch, you get this. Here's part B. Now here's my load. Same length line, it's got a load, same Z0. And now what do I measure as this?
35 plus J85.
Plus J85, all right? Now, hear me on this. We got to normalize it, right?
Mm-hmm.
That's the act. We have to normalize it to see where this point is on the Smith chart. So if we take 35 plus J85 and divide it by 50, what do you get?
0.7 plus J, 1.7.
1.7. You all follow me on that? Let's locate that point on the Smith chart. Over here, where is that? Well, we got 0.7. The one circle is about here, isn't it, class? I mean, it's right there. That's 1. So 0.7 is going to be about there. Take a look. This would be a radius that is associated with 0.7. Can you all see that? In the back there? You got it? Over here? All right, now, the J, what is that? 1.7? Where is that? Well, here's J1. J1.7 is right about here. Can you take a look and make sure? You all see that? That's this trajectory right here. Where does it intersect? Right here. Mark that point. That's ZN, right? Everybody? Okay. Now, here. Now, take a straight. Let's be honest there. See, that's exactly how I feel. I'm a little. All right, so now take your straight edge and draw a line right through that. All right. That's my normalized ZN, right? Take your compass and now do this. Now we're making a circle of that radius. Do y'all follow me? All right? And you got to do me one other solve. You got to do this favor. You got to tell me where this is on wavelengths towards generator. I'm going to use the outer one. Where is that? I can't tell me. Huh? It's going to be 0.1 something, 0.16 maybe.
It's about 0.1634.
1634. All right. Lambda. With me? Now, remember, that has to do with the load here. That's the input impedance we measure when it's normalized. But now we're not going to move wavelengths towards generator. We're going to make wavelengths towards load now. Follow me? The opposite direction. We're at the generator, you might say, right? We're going to go in the opposite direction. How far? The length of the line, 0.065. So subtract that from this, and what do you get? Because I can't tell you that right off the top.
I have about 0.098.
0.098, almost 0.1, right?
Yeah.
All right. Now take a look. Now read the value of the normalized impedance, because that is the load impedance. Do y'all follow me? What is it?
Oh, my thing punched a hole through it, so I can't get a good reading.
Can anybody give that to me? Because I can't do that.
I don't know what we're doing, so
You what?
I'm gonna be real honest. I don't know what you're trying to do right now. So
Okay.
I'm trying to keep up, but
This is not hard. Do y'all understand? Do you understand why I plotted this point?
yeah.
Why did I plot it?
That's the Z N.
With the load, right?
Mhm.
All right. So I plotted it there. Now you understand if that's the input impedance, right? The load impedance is somewhere on this trajectory. You understand why, right?
Yeah.
Right. Now, this has a wavelengths towards generator point, right?
Mm-hmm.
Can you see that? Look at the outer rim. It should be about 0.6 or 1634 lambda, according to him. Can you all see that?
Yeah.
Don't be afraid to ask questions. There are no dumb questions except the one that asks.
I looked at the wrong point.
What's that?
It needs to be 0.17.
Yeah, I looked at the wrong. I have a lot of points drawn on this one. I looked at the wrong point.
All right,
It needs
that's
to
It
all
should be about 0.174, right?
All right,
Is that what you
I
know?
know.
0.174.
Yeah.
0.174. And I'm trying to make sure you guys see this. So
Gotcha.
this is 0.174, and we're going to change this point accordingly. So if that's 0.174, wavelengths towards generator, that's the point where the input impedance is, right? But we had to get there from the load. Well, the load has to be back this way, because if we go from the load to here, in other words, if we had the load impedance, we'd mark that down, and we draw a circle, then we take a look at this wavelength here, and we move it until we hit the end of the line. But we know this, so we have to subtract the length of the line. Can you give that to me? Take 0.065 from
It's 0.109.
right here. 0.109 lambda, is that right? Wavelengths towards generator, is that where the load is? Class? Is that right? Is that, do you understand it now?
Yeah.
You understand why I moved that way? Because that's the length
Yeah, I
of
know
the
why you're
line.
moving that way.
We got the length of the line because we have to move in the opposite direction because we're at the load, we got to go toward, we're at the generator, we got to go towards the load. That's the reason we went the opposite direction.
Okay, so now it's at 0.19. You go draw back down. You get your Z load from
Well,
that. right?
now I need to know what the normalized values are. So I need the imaginary here and the real here, and I can't tell you what they are, but what is it? what is the normalized value of Z load now for this?
Around 0.25.
0.25 and what?
Plus J, 0.7.
0.7?
Yes.
All right, take that and multiply it by Z naught, which is 50, and what do you get? This will be the ZL, which will be what? If I multiply that by 50, I get 12.5, right? 12.5 ohms, is that right?
Yeah.
Plus-
Plus J35.
Plus J35 ohms. What's the answer?
Yeah, that's the answer.
Is it the, okay, y'all see this, class? Now, I'm going to warn you, if you don't, there's subtleties about this, but just remember why we're doing what we're doing. We're going kind of in a reverse order, right? Before we always found the load, then we're wavelengths towards generator. Here, we're at the generator, we're at the input, so we have to go the opposite direction, wavelengths towards load. Got me on that?
Yeah, that makes
And they
sense.
have another one where it's wavelengths towards load. I don't even mess with that. I always just stick on the outer rim because if I start telling you all sorts of stuff about tricks, I prefer all my tricks have to do wavelengths towards generator. You're going to get really confused, in my opinion. Other people do it differently. You okay with this, class?
Yeah.
Did you have another one?
The only other question I have is how did you get the initial like L being that wavelength?
All right, what did he give us for this one where it was a short, right? Right?
Mm-hmm.
All right, what's the impedance of a short circuit?
Just 0, no?
0 ohms, normalize it. 0 to
0.
Still 0, right?
Yeah.
Where's 0 on the Smith chart? Take a look at your
Zero's
Smith
the
chart.
Smith chart, that's all the way to the left, no?
Right here, right?
Yeah.
That's our point where we start at.
Mm-hmm.
Now, how far do we move? Until we hit the input impedance. They said the input impedance here was 25, right?
Oh, that's how you got
So we got to normalize it, J5, or J 1/2, right? That's how we got that. But ask the questions. You probably are not alone. There are a lot of times this stuff gets confusing. And you kind of go, huh?
That's-
And I'm the first to say, I've taught this. This is an undergraduate. At the graduate level with a lot of this stuff when we do time, it gets, I mean, you really need a cup of coffee before you do this stuff. You got to be on point all the time. Random's that way. And he's in my random class.
Okay, well, that value is different than what I'm getting.
What value? Hold on.
The lambda, the 0.065.
Oh, it is?
Yeah, I think that
What? Doggone it. You give me another
I
fake
would not be
value?
surprised.
that value needs to be 0.074.
Is this 0.074? Is
That's
this a
less-
0? This is 0.074?
Yes.
Can anybody confirm? Oh, boy.
I do not have a straight edge, my bad.
0.074. Get your eyes checked.
So now with that 0.074, you subtract it from the wavelength to generator from the other problem.
Now we subtract it from here at this point.
Yeah, from the, okay.
Yeah, that's right.
Gotcha.
Oh, you get 0.1.
Huh?
Oh, no, never mind, it's 0.074. Never mind.
Are you with me on
You
this?
get 0.1,
I'm sorry.
which should be.
Yeah,
I
you get
trust-
0.1.
Okay,
And then-
so it's 0.1 exactly?
Yes,
So this point here is 0.1?
yes.
All right, so this is 0.1 lambda. That sounds like a Wentworth problem. And then you're going to have to read the values, but that's how you do the problem. You good at that? Okay. Can you see it back there, sir? All right, good.
And then,
Another one.
you go down for this point, and that's the point. Okay, that makes sense.
Trust me, you're not alone. This stuff will drive you a little nuts if you try to do it really quick or distracted. It takes, I'm going to level with you, about 2 hours to 3 hours between lectures to stay up with this class in the summer, and especially when it gets really complicated. Right now it's fairly easy, but some of the stuff we're going to hit gets crazy, and so a lot of time for it is what I'm saying. Don't have your girlfriend over when you're trying to work on this stuff. It'll go out of your mind.
Seriously.
And don't watch a ball game. That's the other thing. When I teach this during football season, especially if we have home games, these kids will try to do this stuff at times with all their friends around drinking beer and everything. You're out of your mind. It's not going to happen. One of the biggest distractions I've always felt is the TV when I'm trying to do stuff. Especially if it's something I care about, like a football game or a tennis match. That won't foul me up like nothing else. Do you have another problem for me now?
I don't know. Can we do 227?
Yeah.
I can read it out if you want.
Yeah.
It's a 0.69 lambda long lossless 75 ohm line.
So this is length is equal to
0.69 lambda, and it's 75 ohm.
Characteristic impedance 75 ohms. Go ahead.
And then the Z load is equal to 15 plus J 67 ohms.
C load is 15 plus J 67.
Yeah. It says use a Smith chart to find the reflection coefficient, Visuar, Zn, and the distance between the input of the line and the first voltage maximum.
All right, this is an easy one.
I feel like that's
Because
what we
now
just,
we're going
we've
in
been
proper
doing,
order.
but it's forwards.
So I'm going to draw the Smith chart up here. Just bear with me. So here's my Smith chart. I always try to show you the one circle here, and this is J1 and minus J1 here, right? And this is the infinity point, and this is in 0. So the first step is always what, guys? You asked about it. What's always, if we're given this kind of stuff, normalized impedance, right? So we find out what is ZL is going to be equal to capital ZL over Z naught. And for me, what is it? So that's 1/3, or right? Plus J, what is it? 67 over 75.
It's 0.893.
0.893. Okay, 1/3 for 0.333.
And also it's 1/5, not 1/3.
Yeah, it's 0.2.
Oh, I'm sorry. So it's 0.2.
Yes.
My bad. So where is that now? Just follow me on this. Pay attention. Make sure you see this. Where is 0.2 and J 0.89? Well, 0.2 is about here. Take a look. This is about 0.2 real point. And J 0.89 is somewhere about here. J is 0.89 is about here. So if you take a look at where this intersects, this is your point ZL here normalized. Y'all see that? I want you to do it on your Smith chart. Try to draw it as best you can before I continue. And again, guys, bring a straight edge, a compass, and several Smith charts, because you're going to get this on a quiz this Friday.
Yeah.
Hint, you're going to get it on a quiz this
It's at the
Friday.
bookstore, right?
They have these at the bookstore.
Okay.
Yeah, and you can get the good ones too. Those I don't like is that one. I mean,
I printed 8 of these downstairs.
What?
Yeah, I printed 8 of these downstairs.
I'll give you. I mean,
This floor.
I've probably got a bunch in my office if you need a bunch. But you can. The bookstore used to give them for free, by the way.
Oh,
Really?
Ask them if they have Smith charts. Take one and show them. They used to have these ones, really nice ones too. They were red, very sharp, very useful. But I don't know if they still do. Anyway, so this is first point. And here's what I always tell people to do. Label point 1. That's where you're coming in at. Then take your compass and draw this. You come out from the center to here and draw a circle that big. All right? We're going to... It's a lousy circle, but you get the idea. Follow me on this, guys?
Yeah.
All right. Now this is the magnitude of reflection coefficient. We're going to do it. We're all going to do it. I mean, estimate. Go ahead.
If I do it on the quiz, I can just use these down here.
Yeah,
Right?
yeah,
Okay.
sure. I mean, I'll know if you're doing it right. It's
Yeah.
very, very clear to me. All right, everybody ready? I'm going to make sure.
Draw this out.
Do you have a Smith chart?
No, I mean, but I'm just using the book.
You want a Smith chart? That way, I'm going to hold it. They're not mine, they're his. I'll give them all. I'll give you some Smith charts. Come up to my
I
office.
printed 8, so I've like.
I'll give you a whole bunch up. You come up to my
Everyone come
office.
back and give them back and stuff.
No, don't worry. I got
I
Smith
don't
charts
think I need one
galore.
better.
If anybody needs some, get it from him and I'll pay him back and I'll bring my own. I should have brought a pile down here. That's on me. Are you with me on this? Now, first thing I want you to do, go down to the gamma thing, gamma L on the bottom there, reflection coefficient, and it has REFE usually. And tell me what you get for this.
You just get straight.
Can you do it or not?
Oh, I mean, I just want to
Huh?
give someone else a chance to do it.
Oh, don't worry. They'll get a
Okay.
chance.
So I like the third line.
See what
It's the one that says RFL coefficient and E or I, because E is voltage.
Okay.
and that's what we're.
The longer it is, the closer to 1. Remember that.
I want to say that it's
0.7 something. Did you guess what that?
yeah. I got .78 or something
Anybody
like that.
confirm that?
I got about that without a straight edge.
0.78.
That's your ruler, man.
Somewhere
Yeah.
in that. All right. Now, what's the viswar? That's where it intercepts this.
Around 10?
About 10? Is that right? Now, how can you prove it's about right? How do you get the sanity check? Well, I know viswar is what? 1 plus magnitude of gamma L over 1 minus magnitude of gamma L, right? With me? All right, let's try it. 1 plus that is about 1.78, right? 1 minus that is what? Well, 1 minus 0.78, call it 1 minus 8 is 0.2, right? 0.22. So divide that by 0.22. What do you get? Anybody?
I got like 8.1. It's just the intersection is like halfway between 9 and 10 on my circle.
All right, but you all see this, class? It's about this. We're about right. Follow me?
So viswar is like where it intersects with the axis? or-
Yeah, right here, if you look where it intersects with the axis, you should see somewhere around 8 to 10.
Okay.
I don't know.
I think that's easier, but it also on the top row it says SWR on the bottom.
They'll have it
That
in the
also
bottom
measures
too.
it.
They'll have it on the bottom.
Actually, you're right.
All right, you with me on that?
Yeah.
Okay, now, what else? Oh, yeah, they want the input impedance at the end of the line, right?
Yeah. Do we need to get the angle for the
Yeah, you can if you want. You can get it because if you take this and shoot a line straight through there, you're going to see angular dimensions here. Do you see that? It'll start with 0 right here. You'll see 0, and then you'll see the angle going up. Do you all see that? All right, I don't know what it is, but can you tell me?
When you ask for the reflected coefficient on the quiz, will you be asking for the, well, say magnitude, if it says magnitude, we'll just get the magnitude. If it just says ask
Yeah,
for
magnitude
it,
and angle, but you can estimate it. Look,
Okay,
I
so
mean,
you-
I don't, is this where it is? So take a straight line from the center there.
You just go through it, then you go
and
back.
go through there, right through like this.
Then don't you go backwards by
No,
the
no,
line
you're
bit?
trying to find this is the load, right?
Okay.
Is that the load?
Yeah, that's
I
the
draw it straight through there.
I'm gonna go this way.
Yeah,
So right
all right,
handed.
however you can. You need to go right from the center there through that point. You gotta go through that point. There you go. All right, now out here, that's the wavelengths towards jam, but you see on the inside, there's degrees. They start at 0 right here. See this? Like 10 degrees? This is
Oh,
about,
this is the angle of like this guy?
yeah, the reflection coefficient. So it's about what, 45, here's 50, it's about 48 degrees, 47, 48. Take a look.
Okay.
So gamma L is 0.78, an angle of 48 degrees, approximately, something like that. That's what I got. Y'all get that?
Yeah.
Okay. Now, now we need this input impedance, right? Let's finish this problem. I know I'm about done. All right, how do we get the input impedance?
Hey, wait, I have a question.
Yeah.
Yeah, so I think this is the answer. I recorded the answers from the,
That's fine, go ahead.
and it got about 0.78, but it got an angle of 96 degrees.
Well, maybe
Well, that would be the angle.
That'd be the-
you're reading the outside angle?
That's
Oh,
angle
we
deflection
read the wrong.
coefficient.
I just
Yeah,
read the wrong.
outside
These
one.
aren't the answers. I wrote down some of the answers, didn't write some of the others. So.
Wait,
Yeah.
is it reflection coefficient we're looking for?
Yeah.
That's the outside.
No,
angle.
it is 96.
Oh no, it is 90. Okay, we just read the wrong angle.
The coefficient's the outside one is what it says, right?
Oh, it is, it's right here,
Yeah.
90, yeah.
Okay,
It should,
gotcha.
what am I saying? It is 90-some degrees. It's almost a right angle, right?
Yeah.
All right, I'm
Good.
sorry about that. My eyes aren't as good as they once were. Yeah,
Oh, I don't have a question. I'm just scratching my head.
all right. Y'all with me? Let's get the input impedance. Now what do? Well, here's where we are at the load. We're gonna go, and what's the wavelengths towards generator on here?
It's like 0.11, like 8 or something.
0.118
Yeah.
lambda, can you check that?
Yeah.
that's about what mine is too.
Yeah.
All right, now, the length of this line is what, 0.69, right? So add, and I'm going to show you something, just listen. We're going to add 0.69, but I'm going to show you. So go ahead and add, we want to figure out where we are. We're here, and we got to go that far, but you're going to see something crazy happen. So if I take 0.69, the length of the line, plus 118, right? What do you get? Just give me that value. Pay attention to this, everyone. This is
808, yeah.
0.808 lambda. Is that anywhere on here?
No.
What do you have to do? Subtract the half wavelength. So subtract the half wavelength, and what do you get?
0.308.
0.308 lambda. Where's that? This is 0.25, so that's down here, isn't it? We're moving. We're at the low. We're going wavelengths. So it's about, I'm going to say somewhere out here, is it 308?
Yeah.
0.308 lambda. Can you all find that on yours?
Yeah.
Wavelengths towards generator, the outer rim. Everybody? You know, this is one of these things. It's good to have a good pair of glasses if your eyes are like mine. It's very, you got me on this, guys? All right, now, shoot a line through there from the dead center of the circle through here. And where that intersects the trajectory of your reflection coefficient we drew, remember we drew a circle in there, that's going to be the actual normalized input impedance. Y'all hear me? Take a moment and do it.
So that'd be your ZN, right?
Yeah.
Okay.
But normalize it.
Yeah, normalize ZN,
All
obviously.
right, so tell me what you get for this.
I got 1 minus
1, okay.
1 minus 3.4J.
J 3.4. Can
Yeah.
anybody confirm or deny that?
I got about 0.8 minus J 2.4.
What?
I don't have mine.
This is always trouble.
1 minus.
We don't have the
0.8.
proper.
tools.
Let me see what. Did you draw this? Is this right here?
Yeah, I drew this down
And
here.
this
That's
is
about
point
3.08, no?
wavelengths towards generators, the outer one, right? And so this is 0.3.
A little bit left because it's 0.08. So
308, wow, that's out this way, yeah. A little higher than that, right? 0.308, so that looks right. So I'm getting about 1 there, right? Here's the 1 circle.
that's 1, and
1
then
minus J, oh boy, it fades. What is that? J, that's 3, right? So this would be about J 2.5, 2.8, something like that.
2. Oh, it is 2. Yeah, it is 2. It's 2.
So this is about 2 something, right? 2.5?
Yeah.
Minus J 2.5?
Yeah.
Yeah, 2.6, 2.5.
I got close with that. About 0.8 minus J 2.4.
Again,
Yeah.
drawing tools help. Sharp pencils, good Smith charts, straight edges and compasses all make things work. All right, so for this, that's Zn unnormalized. You have to multiply it by 75. What do you get then? When you multiply that by 75.
Oh, it's 2.6.
It's 75.
75 minus J 187.5.
How much?
187.5.
Is that what he has? Close or not? Anybody?
I'm not sure.
I'm glad this is video. Thank you.
We were unprepared today. Okay.
You will be on Friday because it's a good quiz. And it's going to be on all this stuff. Last couple of, what'd you get?
That's
Hold on.
terrifying.
No, I ain't terrified. Just gotta, hunker down. Huh? Is that the answer? No. What problem is this?
227.
Is that Zn?
ZN. I'm not sure.
The answer is 60 minus J180. So
50?
60.
Okay, we're close, but we got a lot of fudge in there.
Yeah, that's what I got.
Why?
Oh, that's just what I got.
All right, well, I'm going to tell you, go through that problem and see where your fudging is, because obviously the Smith chart stuff is not exactly one of these things you want to bet the ranch on.